So today's topic is solution method for elastic problem. Actually, we learned a lot of things about strain, stress, and some equilibrium, right? The final goal was to find the solution. So today's topic is very important, right? So without knowing the solution method, we cannot solve the elastic problem, right? Okay, so in this class, we only interested in the important problem in engineering. So I don't want to consider the nonlinear. Okay, so I want to only consider linear elastic. So first, the important assumption is a small perturbation. So small perturbation means everything is small. So small deformation and small displacement so small, actually deformation and displacement has the same meaning, right? Almost same, sound same, but both are actually different. Formation has a meaning of relative displacement. Okay, so that's the small difference. So small deformation means the gradient of displacement is small, smaller than 1 for all material point X. So at all the position in the body, the gradient of displacement about the space is small. Okay? And small displacement itself is small. Compared to some characteristic length LC here is small. So this is a characteristic length. So characteristic length depends on the problem you are considering. So in cantilever beam problem, the length of cantilever beam, it can be a characteristic length. Ship, length of ship. So if you have some solid like a sphere, the radius can be a characteristic length. So we are saying that the other length is overall length. So you can think the biggest size of the body. It can be one of important characteristics. Right? So you can think this size of structure. Okay? So compared with the size of structure, displacement is small. Much smaller than total size of structure. Then we can say small displacement. And also, we are considering the rho. Rho is density. Actually, density is a function of space and time. But we will consider density doesn't change about time. So density is only function of space, right? This is a very widely used assumption. So now I think you understand the small difference between deformation and displacement. Okay? Deformation is a gradient of displacement. Displacement is just displacement. Difference between position, right? And measure of deformation is what? Strain, right? Okay, so now let's summarize the governing equation. So first, in the body, we have a local equilibrium equation, divergence, and here F minus, I think, gamma, low 0, gamma was 0. Or in tensor form, plus equal 0. This was a local equilibrium, you remember? And second, so this equilibrium should be satisfied in all the body, right? All the position at all the position of the body, and on the surface. Surface can be divided by two parts. Okay, so one is force boundary. Okay, traction is applied, and on displacement boundary, so some displacement is applied. So on the force boundary, this is equilibrium. This equilibrium should be satisfied, and displacement boundary, displacement should be prescribed, same to the prescribed displacement, right? And third, material law. Stress equal material constant I plus 2G, and in tensor form KK IJ plus 2G EIJ. Right? Of course, we have a relation between strain and displacement, right? Strain is a function of displacement, right? We need to consider this equation too. So when we solve the elastic problem, we need to consider all of these. So the solution should satisfy local equilibrium force boundary, displacement boundary, material law, strain displacement relation, right? Lot of equation and lot of condition should be satisfied if we have a solution. Okay? So solution procedure looks complicated, you think. It could be complicated. So in our problem, so linear elastic problem, okay, actually problem description. Description. So for elastic problem, we have a given. What's the given? First of all, geometry and boundary condition. So I like say just BC. And material property. So we know the shape of body, we know the force boundary and displacement boundary and material property. For example, we know the Young's modulus, and we know Poisson ratio. Okay, then we can solve we can find the solution. Find stress field, strain, displacement. Actually, field. Field means stress is a function of position. So, all the stress at all the position. Solution. So, from these given conditions, our goal is find the stress strain displacement. Okay, so and to solve this problem, we need to use governing equation. Right? So you are already very familiar with governing equation because we spent more than 1 month to explain all the governing equation, and we derived many of those equations before. So there are two different solution procedures I'm going to teach today. Both are very important, and two big stream in mechanics. The first, solid mechanics. So first, displacement method. So displacement method have a known and principal unknown principal unknown is a displacement field. Displacement. U. So this is the principal unknown. So there are stress, strain, and displacement. Which we need to find. So in displacement method, first we start from the displacement. So and we change all the stress and strain in terms of displacement. So name is displacement method. So procedure start from the displacement. And then once we know displacement, we can calculate the strain, right? Because we know the relation between strain and displacement. So strain transport, okay. Then we can find the stress, right? Stress G. Okay, so here we start from the displacement. You can express strain in terms of displacement, and then we can represent the stress in terms of displacement, right? Through this procedure. And next, we put that stress into local equilibrium equation, right? So local equilibrium equation can be represented in terms of displacement too, right? So local equilibrium equation has a form of partial differential equation, right? This is differential equation. So how we need to solve differential equation in this stage? How can I solve? There are many methods, but simple procedure is integration. So once we integrate this equation, integration, so differential equation, if we integrate the differential equation, we will have a what? Integration constant, right? C1, C2, C3, something like that. Then now we need to find that integration constant. How? By using boundary condition. Then solution. Here, solution. Here we need to use boundary condition. So here the solution means the displacement. So because we start from displacement and primary solution is displacement, once we know the displacement, we can easily find the strain and stress, okay, by using these two equations, right? This is very straightforward procedure. Here the key point that how we assume the first displacement field. The starting displacement is key. So starting displacement is correct, then other procedure become very simple. But so first step is always the most important. And other procedure are automatic. And the other method is named stress method. So stress method, of course, name is stress method. Principal unknown is stress. So stress. Maybe you might ask me why there is no strain method. But stress method and strain method are both the same thing actually. Because between both there is only one relation, material law. So, but people like to use stress method. Okay? So principal unknown is stress. So starting point is stress. First, we start stress. Because stress is the main unknown, then we need to find statically admissible stress field. You know how to find this, right? Because I gave you example before. So statically admissible stress field satisfy the equilibrium equation in the body and on the boundary. Right? This is statically admissible stress field. Of course, in displacement method, when we find the displacement field should be kinematically admissible, right? And so once we found the statically admissible stress field, we can calculate strain from the inverse relation between strain and displacement. This is material law. Right? We can use material law. Then we can find the strain. So now we can express the strain in terms of stress, right? And we can express the from that equation we can find displacement. From the displacement and strain relation. Transpose. Okay? So, from here, we can find relation between stress and displacement, right? Stress and displacement. And here, now, we can express the displacement in terms of stress. So, next step is this is also differential equation, right? So we need to do integration. And solution. They're going to be integration constant, right? Then we can find that integration constant from the displacement boundary condition. So these two methods is really basic and important in solid mechanics and structural mechanics. So the other name of stress method is force method. Same thing. Force method, stress method are same thing. So only difference between two methods are the what is a principle unknown. So long times ago, some people try to develop the displacement method. Some people focus on developing the stress method, but finally the winner was a displacement method, because that method is a little more simpler than this. So nowadays we are using dominantly the displacement method. Finite element method is also based on displacement based method, but in some analysis, displacement method has some disadvantage. So some people try to use mixed both. Okay, so we are saying that's the mixed method or hybrid method. But in this class, I don't want to teach that kind of method. Okay, so this is a displacement method is most important. So you understand the procedure. It's quite straightforward, right? But without showing the example, you never. It's very hard to understand. So I'm going to show you very easy example, and you will solve little bit complicated problem in midterm quiz exam. Okay. Okay, so the example. We have a solid medium here. Okay, at the bottom we have a rigid surface. This is a rigid, so rigid surface. Rigid means undeformable. Deformation is not allowed. And here we have a solid medium. And at the top, we have a pressure P. Pressure P, top pressure. And depth of the medium is H. And I'm going to consider x direction is this, EX. Okay, so at the top x equals 0, at the bottom x equals h. And y and z direction, the size of domain is infinite, right? So really big. So infinite in EY, EG direction. That's not infinite, then the problem becomes very hard to solve. Okay, and I'm going to give you one more. So density 0. Zero density. So problem very simple. At the first stage, you should think how this solid body will deform. how this solid body will deform. Just think. First, the thinking stage is very, very important, right? So you have an engineering sense, right? Through your engineering sense, you need to guess how this will deform. This place will be function of, in this case, function of y. It can be function of y, g. Okay, this placement will be, in this case, only function of x. Because of this is a infinite domain in y and z direction. So, and only pressure is applied to an x direction, right? This will make a deformation something like this, right? So deformation, displacement will be happen in only x direction, right? So we can assume u is a displacement x. This will be this displacement field. Of course, you can assume y and z displacement here, but in final solution, they will be disappear, right? Okay, so we start from this displacement field. Then, second is a strain. We can calculate the strain. Strain field will be very simple. U 0, 0, 0, 0, 0. There will be only strain in x direction through the thickness. Okay, and from this strain we can calculate stress field. Stress field from the material law. Okay, then lambda plus 2g 0, 0, 0, 0, lambda 0. Oh, sorry. Lambda 0, lambda 0, 0, 0, lambda. This is stress. So you can express the strain in terms of displacement, stress in terms of displacement. X, U. Now we need to apply local equilibrium equation. Right? Stress XX, YY, GG. We have only three stress. So we can apply the local equilibrium equation, then we will have three equations. But all this stress is only function of S, X, so we will have only one local equilibrium equation, which is not trivial. XX is 0. This is a local equilibrium equation. Okay, this is just a one-dimensional problem. Then this means lambda plus 2g here right? So now we have a second order partial differential equation. So we need to integrate. Integration. First, okay, so lambda plus 2g partial x c1, right? Once, if we integrate for one time, we can have a constant and equal lambda plus 2g c1. Let's integrate one more. U equal lambda plus 2g c1x plus c2. In this stage, we need to find the integration constant c1 and c2. Okay, boundary condition. Now we need to apply the boundary condition. Okay, two boundary condition. First boundary condition, false boundary condition. Stress and here this is boundary. Surface direction is here minus EX equal PEX, right? This will give stress XX equal minus P at x equal 0, right? So stress XX equal from this equation lambda plus 2g partial x partial u, okay, equal minus p at x equal 0. Okay, let's use this condition. Then we can find the C1. So let's put that equation over here in lambda plus 2g and lambda plus 2g C1 equal minus P. So C1 equal minus P. So C1 equal minus P. Right? C1 equal minus P. Now we need to find C2. This is a false boundary condition, false. And boundary condition, displacement. What's the displacement boundary here? We have a displacement boundary at the bottom. So at the bottom, displacement, no displacement. So U H equal 0. So U equal minus P lambda plus 2G H plus C2 is 0. So now we can find C2 equal lambda plus 2G minus PH. So now we found the C2. So finally, solution. Finally, displacement U equal U x E x equal lambda plus 2G minus P x minus H E x. This is a displacement field. Solution. And of course you can find strain. What's the solution for strain? Strain x lambda plus 2G minus P 0, 0, 0, 0, 0, 0, 0, 0. This is strain and stress. Okay, stress lambda plus 2G lambda plus 2G minus P. This is stress field. So if we look at the strain, we have only component strain XX. But if we look at the stress, we have a stress XX, YY, GG. Right? We have stress YY, GG. Because of the Poisson effect, right? So this medium wanted to expand in Y and G direction, but cannot expand. Due to this, we have a stress YY, GG. So even I didn't remember in the solution procedure what final stage is that to check whether the solution is feasible or not. Okay? Okay? Finally, we should check it. So that solution is satisfying all the governing equation and boundary solution. Right? Okay, this is a displacement method. Any question? No? So we can solve the problem directly by hand. If the problem is simple like this, but problem become little bit more difficult, it's almost impossible to solve by hand calculation, right? We need to use some numerical method. Okay, so now you understand. displacement method. Okay. Next, stress method. Same problem, but I'm going to use stress method. So first of all, we need to find statically admissible stress field by using local equilibrium equation and boundary condition. You remember the example, 2-layer soil problem, right? At the time, we try to find the admissible, statically admissible stress field. That's the first step we need to do, right? So once we do that step, we can find the statically admissible stress field have a shape of this stress XX, stress YY, stress GG. It has a shape of this. Okay? And here, stress YY and stress GG is the same. But in Y direction and G direction, problem is symmetric, right? So same stress in Y and G direction. But in X direction, different. So actually the first step to find this is not that easy if the problem is very complicated, right? And of course, in this case, we can easily identify stress will be only function of X, not the function of Y and G. Same stress field in Y and G direction. If the position in X direction is the same, right? And statically admissible field will give us stress XX is minus P if you apply the boundary condition. So stress minus EX equal PEX will give us stress XX is a minus P. So finally, stress tensor looks like this: sigma YY, stress YY. Because stress GG is the same to the stress YY. Okay, so until this step, to find this statically admissible stress field, statically admissible stress field. To find this statically admissible stress field, we already used local equilibrium equation and force boundary condition, right? Then we can find this stress field. The next step. We need to use material law. Then we can calculate strain. So in this equation, I like to use material constant, Young's modulus, and Poisson ratio. Okay. And this equation results in the minus E P plus 2 mu XX. This is strain field we can find from statically admissible stress. And then displacement U. In displacement is only function of x, ex. So minus E P plus strain XX will be U equal over there minus E P plus 2 Poisson ratio sigma XX. Right? So here, if we integrate this equation, we can find the displacement U minus E P plus 2 sigma XX and constant X plus C. X plus C. And also strain YY equals 0. Equal over there E YY plus YY minus mu YY plus mu P. This is 0. So what's the unknown here? We have two equations here. What's the unknown? Unknown is here constant C, material constant C, and stress YY. Right? Because we know stress XX already. Yeah, this should be YY. This is something no. YY. Here YY. Right? And let's solve this equation. Then we will find the relation between stress YY and P. Because the strain YY is 0, then stress YY equal minus 1 minus Poisson ratio P, right? So we can find the stress YY from the second equation. Then displacement U become E1. Equation become little bit complicated. Here, Px plus C, material constant C. So now we have only one unknown C. How can I find that? We know the displacement boundary. Displacement boundary condition UH equal 0. Then finally we can find displacement field U minus E square P x minus h. This is displacement. Okay? So, for the displacement method, U was expressed by lambda in G. So, it was minus lambda plus 2g1 p x minus h, right? Both are same thing, same result. Okay, because we know the relation between lambda g and e and mu, right? If you use that relation, this equation become like that, this equation become like this. So both are same. So, which method do you like more? Any question? No? Okay, so finally I'd like to give you a simple theorem of superposition. Theorem of superposition. So, in linear analysis, we can use theorem of superposition. Okay? So, for example, I like to give you simple example. Here we have a linear spring and have a constant K and displacement u and p. So relation between p and u is like this, with a slope k, right? So at the first time, I'm going to pull this with a amount of force P1. And then we will have a displacement U1. And second time, so I'm going to apply P2, the other pulse, then U2, then displacement U2. Then third time, I'm going to apply P1 plus P2. Then what's going to be a displacement U? What's going to be a displacement U? Displacement becomes just simply U1 plus U2. This is for position, right? Input, if you plus input, output become the sum of both input. This is the only hold for linear analysis. Okay, actually, linear have a meaning of this. So first case, we apply the P1 here, and this is this U1. And P2 here, this U2. If we apply the P1 plus P2 here, this will be U1 plus U2. Because the relation between P and U is just linear. This is a theorem of superposition, and this is just one-dimensional example, but same thing can be applied for general 3D case. Okay, so for example, let's say we have a same geometry here, same geometry and same solid and same material property. Then we can apply. We have a different external load and different prescribed displacement and different body force also. So different G gamma, rho gamma, different body force. So this is case 1. So these three are all the boundary condition, force and displacement boundary condition. For the case 1 is give stress, strain, displacement of case 1. This solution. Here, same geometry and material. And this is the first case and second case. Second case will give a different solution, U2. Then third case is that sum of this. One, two, three. So, okay. So this give a solution lambda 1. Lambda 1 and lambda 2 is some constant. Right? This is a superposition theorem. So here you can apply here alpha 1, alpha 2, alpha 2. It becomes just alpha 1, u1, alpha 2, u2. Alpha. Okay. This proposition theorem can be used for only linear analysis, right? Non-linear analysis you cannot use, okay? You should remember. Okay, so I'm going to finish today's class now.